This video is going to cover the concept of finite state machines, and I think you'll see why it's called finite state machines once we see an example or two of this. I will say that this is not directly in part of graph theory that we did before. It's a slightly side topic here. It is, however, crucial in understanding the nuts and bolts of computers and how they work. Most of the time when people are learning programming languages, they're learning high-level languages, and they don't even stop to think about how the computer is actually performing these calculations, and as a result they'll write code that is not super efficient and might be slower. With modern day computers, that's not that big of a deal in most situations, but there are definitely times when you want to truly optimize what is going on, and to do that you have to work in a lower level situation. And if you go all the way low level down to logic, that's where you're going to be dealing with finite state machines. And so this is going to introduce the concept here. So our first example problem is going to be the idea of a vending machine. I made some assumptions to make our lives a little bit easier, but you could certainly make a vending machine in any situations in this type of process. Just your picture is going to be much more complicated. So the idea is that my vending machine only has one item, and that item costs 25 cents, and you're allowed to enter only nickels, dimes, and quarters. And as soon as you've entered a total of 25 cents, it will go ahead and spit out the item that you are doing here. I'm also going to make an assumption that you never put in more than 25 cents. Then we'd have to deal with giving refunds and things. I don't want to do that in this particular problem. Again, if you were going to design this in the real world, you would take things like that into account. So here's the idea. We're going to say, well, at the beginning state, the beginning situation that our vending machine is in, at this point in time, nothing has been submitted. So I'm going to call this state 0 because currently there's 0 money in the machine. Now, at this point in time, there are 3 things that could happen. They could put a nickel in, and I'll put a little 5 here. They could put a dime in, or they could put a quarter in. And I'm going to go ahead and name the new places we're at based on how much money we currently have. So this is state 5, state 10, and state 25. Now 25, that's going to be our final state. That's where we want to get to. Now if I had first put in a nickel and I put in another nickel, then I will now be in state of having 10 cents. However, if I first put in a nickel and then put in a dime, I would now be in the state of having 15 cents. And if I first put in a nickel, then put a quarter in, as I said, we're going to assume that you never put in more than 25 cents, so that's not going to be a possibility. We're not going to draw it in here. Okay, so now that we have that, we're going to go ahead and look at the next part here. We're going to say, okay, if you're currently at 10 cents and you put in a nickel, you'll be at 15 cents. And if you're currently at 10 cents and you put in another dime, you're currently going to be in 20 cents. If you are currently at 15 cents and you put in a nickel, you're going to be at 20. And if you're currently at 15 and you put in a dime, you will then be at 25, so you're good. And the last one here is if you're currently at 20, you put in a nickel, you get to this. So this right here is a finite state machine diagram. It does look similar to a directed graph, but it's not quite the same thing. These numbers that are on the arrows, these are not the weights that we saw before. These are simply the input of the machine that's causing it to change from one state to the next. Again, there are a lot of other things that are possibilities here in that, if you go over 25 cents or whatever other things may happen, what if you wanted to enter pennies in here? You'd have a lot more possible states of values in the machine. It'd be a real big hassle. Also, sometimes in state machine diagrams, you want to put an output as to what the machine's going to say each time. So for example, if you get to 25, you could put a little y as the output. Is it yes, it's going to give you a item from the vending machine, and then every other state would have a little n next to it, because no, it's not going to give you the output. And usually the way we write this down is put a little slash here. So this would be like 25 slash output y, and so on. That's called finite state machines with output. But this is the general idea. The general idea is you write down these little circles, and these are called states. These are the state of being that the machine could be in at any given time, right? And so then what we're trying to do is we're going to say is, how do you move from one state to the next? And we're trying to describe it in as simple as possibility as we can. Sometimes you could have many more state diagrams that all work for the same problem, but the simplest one is going to be considered the best of them. And so let's look at the second problem now. For the second one, I'm going to only use a binary system. It will make our lives a little bit easier here. And that's really just what we want to deal with at this point. Computers deal with the binary anyways. And some people talk about this as recognizing a language. I'm going to say it's a password here. So what I'm going to do is I'm going to have a starting state. I'm going to call this S1. This is my starting state here. And the idea is I want to see what happens as I enter in my password. Now I'm going to assume at first that I entered in perfectly. So the first thing I enter, the input, is going to be a 1. I will call this state 2. Then I'm going to enter 0 for the second one. I'll call this state 3. Then I'm going to enter a 1. We're going to call this state 4. And finally a second one. This will be state 5, and that's going to be the finished state. So if we get to state 5 here, at this point that means that the password is correct. Now let's look back at the beginning here. Let's suppose at the beginning, instead of typing in a 1 first like you're supposed to, you typed in a 0. Well, if you start typing a 0, you're wrong, so we should go right back and say that we haven't typed it in correctly, and we get to start over again. Now for the second one, let's suppose I type in a 1 first. So my first digit is correct. And then I type in a 1 a second time. Well, that's not going to work, because if I type in a 1 a second time, it knows that I have not done the password correct. Now, I want to draw something here to show you something that makes this problem more complicated than we'd like it to be. So this is the correct password here. And now what we're going to do is we're going to assume that someone goes, okay, 1, and then they hit a 1 again, and they realize, oh wait, I shouldn't have done 2 1s in a row. Let me go back here, and I'll now consider this to be my starting point and say 1 0 1 1. Because this does include the correct password, we want to make sure that this is allowed. This should be a valid entry here, even though it ignores the first one. That was a mistake at that point. So here's the thing is, if I go back to the beginning after I do the second one, then it's going to get a 0 and it's going to think it's not correct. So what we have to do is we have to modify this and say, if we've entered a 1 here and we enter another 1, I'm going to go back to state 2 and think of that second 1 as the beginning of the correct password. So that means at this point we're back into the place where I have one thing correct on my password. And if you keep hitting 1 1 1 1 1 over and over again, it's going to keep staying here until eventually you hit the 0 1 1, and then the thing is going to unlock. So it's a little tricky here why we should do that. Definitely you want to practice this so you can see why I went there. But let's say we have that. So now we know that if you have a 0 1 at the beginning, what we do, we have a 0 1 here, what do we do, and we go to this one. Now, at this point, when you're in state 3, if you hit a 1, that's the correct one here. But if you hit a 0, we need to see what happens. So let's suppose I've already done 1 0 correctly, and then I hit a 0 next. right? That's what I'm at this state and I hit a 0. Well, at that point in time, that could not be any correct beginning of the password. 0, 0 is never going to happen in the password, so that means I need to go back to having had no things correct. And then we have one more thing to deal with here, and that's if I'm currently at this state and I enter a 0, that means you've done 1, 0, 1, and then instead of having a 1 next, you put a 0. Well, I can consider this to be the beginning of the password. So I want to go back to the state where I've done a 1, 0 so far. So that would be right there. And then if you really want to be complete here, you can say that once you've entered the password, it doesn't matter what else you enter in, and it will stay unlocked here. And so this right here would be a state machine diagram for detecting the password of 1011. And again, this is a pretty subtle concept here, exactly where all the arrows should go. We are simplifying a little bit, making it so it's binary, so that each one will only have two possible outputs, or sorry, two possible arrows coming out of it. The 0 arrow and the 1 arrow. So this is what we're going to have here. Okay.